Okay, good morning and welcome everyone. So, so this is the final workshop for the summer cluster. I think many of you have been here already for the summer cluster and hope it's been stimulating. But, and welcome to those who've come here just for this workshop. Okay, so let's see a few things, a few announcements about and just some general background. So first of all, I think most of you know the summer cluster is organized by the Quantum Pod at the Simons Institute, and you know this. In some sense, I think all of you know about the Simons Institute, but maybe if I were to describe it in a sentence, you know, the Quantum Pod sort of embodies the organizing principle of one of the main organizing principles of the Simons Institute, which is this computational lens on the sciences, which our activity very much represents. Okay, in turn, you know, the Quantum Pod is sponsored by this NSF Quantum Leap Institute, the CIQC, and a grant from the DOE. So, for those of you who took part in the summer cluster, at some point late this summer, you will receive an email from Caroline asking you to acknowledge, acknowledge those grants and any publications that result from your time here. Okay, let's see. Let me just get to finally a couple of last notes. So, you know, the organization of this workshop took a lot of time and effort, and the organizers. Nico Breukman and Urmila Mahadev and Anand Natarajan. So they spent a lot of time and effort on it. So I hope you'll enjoy it. And then secondly, you know, pulling the cluster and the workshop together takes a lot of effort from the staff who work behind the scenes. And so they include Francis and Ashley from events, Atia, who supported all the long-term visitors, and Drew, Joe, and Omid with AV. Omid is in there helping us right now. So maybe a round of applause for all of them. Okay, and we are starting today with John Bostanci, who just finished his PhD at Columbia with Henry Yuan, and he actually just also joined the Simons Institute as a Simons CIQC postdoc. John is going to speak about one of the eye-catching results from this last year. So,
well, thank you. Yeah, thanks for being here, and I'm excited to talk about this work. Hopefully the talk will be very understandable, and I tried not to have too much like math, so yeah. Okay, so since we're at Simons, I figured I didn't need too much of an introduction, but I did put a little bit. So, you know, when we talk about like proofs in computer science, you know, I think most people who don't do quantum computing would think about this very famous problem, which we call P versus NP. So it's kind of like we're trying to, you know, in the P versus NP problem, we're trying to understand the relative power of like classical algorithms that are efficient and like algorithms that get like some unbounded proof, polynomial-sized proof, but that can be created by an unbounded prover. And you know, I do quantum computing, so it's sort of natural to just like replace all the efficient quantum algorithms with efficient classical algorithms with efficient quantum algorithms, and you get sort of this. You know, this is like a diagram, but I don't think people study this too much because back in like 2000 and like the early 2000s, people like noticed like, well, we switched you could switch the algorithm to be quantum, but then like you don't need this proof to be classical anymore. You could have it be a quantum proof. I think, actually, I don't know, there's some history. Like it first appeared in your like class in 2002. Sorry? Like QCMA versus, like the definition of QMA and QCMA, it was like in your class in 2002. So yeah, anyway, so like you can define lots of variants of quantum NP, but sort of the two interesting ones for this talk are going to be the variants where the prover has to send you a classical proof or the prover gets to send you a quantum proof. So these are called QCMA versus and QMA. And yeah, also there's like some history to the naming. I think QMA was discovered first, and that's why it has a shorter name, but maybe, I don't know, QCMA kind of sounds like a weird name to me, but that's what they're called. It stands for like Quantum Classical Merlin-Arthur and Quantum Merlin-Arthur. Okay, so this is what we're going to be talking about today. Hopefully that very quick introduction to this problem made sense. So the first thing you might try to ask is like, well, could we just separate these two classes outright? Unfortunately, they're both like in between P and P space. Also, I put a lot of effort into making this P space guy with the laser eyes, so hope you appreciate it. So, until we separate P and P space, we're probably not going to be able to separate QMA and QCMA outright. So the next best thing would be to give some like evidence that they might be separated. Typically in complexity theory, this comes in the form of an oracle separation. And I'm not the first one to, think about this. Actually, this problem is kind of, it has a very long history starting in 2002, when it was like the two classes were first like defined by Aharnav and Nave. And sort of the interesting thing about the history of this problem is that people have tried to come up with sort of like a standard, like if it was just like a function in the sky kind of oracle separation. But it's been tricky, and instead what people have tended to do is to come up with like variants of oracle separation. So this Aronson-Kuperberg paper, they studied the QMA versus QCMA problem, and they actually like defined this notion of like what would it mean if there was a unitary in the sky. So like if we allowed people to query a unitary oracle and improved a separation relative to that. And then there's been a lot of works that have like defined more and more classical looking oracles, so like in-place permutations in 2015, and then like these distributional oracles, and then recently there's been a bunch of proofs that sort of like either make conjectures or put bounds on the verifier, like beyond being efficient. But this work is going to talk about actual, like a standard classical oracle separation between these two classes, and it's actually going to talk about two of them. I kind of tried to separate the talk into things that are shared and then like things that are different about the two oracles. And yeah, so before I get into it, I'll just say a little bit about why I care about QMA versus QCMA. And you might disagree or agree with these points, but first of all, I think it would be very surprising if if you could verify the ground energy of local Hamiltonians without a quantum state. Like if there was somehow some very efficient way to represent these things that didn't require me sending you a copy of the ground state, that would be really surprising. And either way, like if there was or wasn't. And I think understanding like oracle separations, like of course I'm not going to claim that like tells us why or why not these are efficient or possible to represent or impossible to represent using classical strings, but they do give us evidence about like, oh, if you did want to show that QMA was contained in QCMA, you should at least look at, your proof has to like use this part of the local Hamiltonian, or it can't like just use it in a black box way. And separately, like it gives us, gives us evidence about like what kinds of Hamiltonians or what kinds of properties of the local Hamiltonian or QMA complete problems like might make them require quantum states. This is true of like basically every oracle separation. The thing that, for me, I care about QMA versus QCMA a little bit more is that a lot of properties that we want to use in quantum cryptography, like non-collapsing, hash functions, unclonability, untelegraphic ability, they kind of appear as like prerequisites to QMA versus QCMA. I think my friend Barak calls them like non-classicalizing properties. But these are like at least like requirements. Like if you gave me a quantum state and it was sort of like classical, or like was possible to represent classically, it would be clonable, telegraphicable. It would be collapsing. or like the problem would be collapsing. So in order to get a separation between QMA and QCMA, we first have to like figure out how to build these things into an oracle. So this is kind of like a test bed for like a lot of the things we would hope to build in quantum cryptography. So that's another reason why I personally like care about this this problem a lot. Okay. And finally, before getting into things, I'll just say a little bit about why I think this problem has been so hard. And again, there's only going to be 2 bullet points, but the first one is that sort of I think people haven't developed too many techniques for separating quantum and classical proofs. So like the proof technique that most of the prior works go through is like, oh, well, let's just guess the witness and then try to argue about the algorithm that you get after you guess the witness. But for many problems, you can guess a quantum witness and you can also guess a classical witness. So it's kind of like, it's hard to distinguish between the two if your first step of your proof is like, well, I'm just going to guess what the witness would be and then try to argue about the algorithm that I get out of that. And the second thing is kind of more particular to QMA, QCMA. It's kind of like, if you want to separate QMA from QCMA, you at least have to argue that the verifier is not just going to measure their proof immediately in a standard basis. Because if they just took their proof and measured it and then did something, then the prover could just send you the measurement result, right? And then whatever they did, they would do all the same. So somehow the problem has to have some kind of structure that makes it so that the verifier wants to like, keep their quantum state around and do some funky transformation to it without measuring it. But then you kind of run into this problem, which is that quantum algorithms are actually really good at identifying or playing with like global structure. So sort of when you start baking in like lots of structure into your problem, you run into this other problem, which is it becomes really hard to argue that like BQP algorithms can't like solve the problem you're trying to talk about. So for a lot of problems we have, like we can prove that like BQP algorithms can't solve problems for random functions because somehow they have so little structure. Like how would quantum help you? But for a lot of structured problems, like quantum algorithms are surprisingly good. So you kind of run into this like you're stuck between a rock and a hard place. But I'll tell you, like this talk will go through some ways that we get around this. So okay. I'm going to start this problem with like a kind of parable about a fisherman on the sea. I'm going to just talk about like how we can get a QCMA lower bound for some problem. Just think of this as like half of the proof, but we'll see that it's quite far from the whole thing. So in this parable, we have a fisherman, he's on the sea, and he wants to know how many fish there are in the sea. Okay? And the way that he gets to check is he can fish. And we want to know like how many nights will he have to fish to tell if there are many or few fish in the sea. Okay? Think of the fishing as like kind of querying the oracle. The ocean is the oracle, and places that are fish are 1s, and no fish is 0. I'm assuming the fish don't move around, but don't worry about it. Okay, so in a little bit more detail, the input is going to be some oracle, which tells you about a set S. Think of it as a fish are, and a size L. So there's going to be a lot of fish, but they're still going to be like relatively sparse. Like not every point in the ocean will have a fish in it. And he wants to know if the size of the set is bigger than L or less than L over 2. Promise that one of the two is the case. Okay? Remember, we're trying to argue that like the algorithm that gets a QCMA, so like gets a classical witness, cannot solve this problem. And so we'll just start by saying, like, assume for the sake of contradiction that he actually can solve this problem. Okay? So let's assume for the sake of contradiction we have this fisherman. He gets a classical proof, and when there's lots of fish in the ocean, he says yep or yerp. And when there's not that many fish in the ocean, he says no or nerp. And let's just go to the very extreme, right? So if he solves this problem,
do you think the size of the ocean figure anywhere in this?
No. Yeah, but the ocean you should think of as exponentially large. So he can't like fish everywhere in his life, say. Yeah. Yeah, so just to say that again, the ocean you should think of as like a really big set, so a subset of 2 to the n, like all the bit strings in the actual problem. And we want to know if he can distinguish between these two in poly n, so poly little n time, or queries. Okay, great. Yeah. So remember, we're assuming for the sake of contradiction, he is able to solve this problem query efficiently, and we'll go to the very extreme. So if he solves this problem of distinguishing between if there's many and few fish in the sea, he definitely must say no when there are no fish in the sea, because that's smaller than L/2. And when I put lots of fish in the sea, he should say yes. Okay. And one important observation is that if he never catches a fish, so if every time he goes to fish, every night for the poly n nights, he doesn't catch a fish, so he sees 0 from the oracle, then in the yes case, then he would never be able to distinguish the yes and no case, right? So if he was in the ocean with lots of fish, and he always saw 0 when he queried the oracle, when he went to go fish, he wouldn't be. He would say the same thing as if he was in the ocean with no fish. So imagine putting him in a pool. Okay, so this is like, we're going to like simulate him. So we don't actually want him to swim in the ocean. We're going to use this fisherman to build another algorithm. And when I say simulating him in a pool, I mean we let him move around as if he was in the ocean. We kind of like think of it like one of those infinity pools where he gets to swim around, but doesn't actually move in a big ocean. And anytime he goes to fish, we just say no fish. Okay, so if he fishes, we tell him there wasn't a fish there. And let's just like see where he goes to fish, right? So if he had the real proof that Merlin would have given him, then he's very likely going to catch a fish. Like if he was in the real ocean and he was able to distinguish between the ocean with many fish and the ocean with no fish, when we put him in this pool and look at where he wanted to fish, he will probably catch a fish. Because if he was unlikely to catch a fish, he wouldn't be able to distinguish between those two cases. Okay? So we'll just study him, and we'll say, okay, he's about to fish at position x1. Okay? Then we can say in our heads, okay, there probably would have been a fish in the ocean at position x1, because he was probably going to catch a fish. And now we'll run this back. So we know that there was going to be a fish at x1 with high probability. So imagine like the version of the problem where we just put one fish at x1, the place he wanted to fish, and we compare him to the ocean with lots of fish. Again, there's only one fish in this ocean, but it's at the spot he would have fished at, so he has to say no. There's only one fish. And here there's lots of fish, so he has to say yes. And again, if he doesn't find another fish in another spot, then he can't distinguish between the two. So maybe he fishes at x1 all the time, he always catches a fish, but that could be the only fish in the ocean. So he has to go out and find another fish in order to distinguish between these two cases. And again, we'll put him back in the pool. And this time, when we simulate him, if he tries to fish at x1, we'll just tell him there's a fish there. And anywhere else he tries to fish, we'll tell him no fish. And by the same logic, he's going to go to a different position, x2, and probably catch a fish. Okay, so if we study where he wanted to fish, we'll probably, in reality what we're going to do is stop him at a random point in time and ask where he was going to fish. But if we do that, he'll probably have to know about position x2 where there'd be another fish. Hopefully that makes sense to everyone. And the point is, we can repeat this many, many, many times. So actually, you can imagine repeating this a super polynomial number of times. And every time we ask him to catch a fish, we record that he wanted to fish there, and then we add that fish to the fake ocean. We can do this up to L/2 times, right? Because he always has to keep, as long as we've put fewer than L/2 fish in the fake ocean, he better say no. And in the big ocean with lots of fish, he should say yes. Okay, so at some point, and this is sort of the part where I'm going to gloss over some of the math, but at some point, if we ask him for a super polynomial number of fish, it's going to exceed the size of the proof that he could have gotten from Merlin. So he's received some relatively small proof, and we've asked him for a super polynomial number of locations of fish, and that would just be a contradiction. There's no way that small proof could have encoded the location of so many fish if the fish are in the real ocean, they're kind of in randomly chosen locations. So that's a contradiction, and that will end up ruling out QCMA algorithms for this set size problem. Okay, so hopefully that made sense to everyone. Just to
yeah. What did the pool represent here? Did it represent given the proof that he gets? What are the places in the ocean he's likely to query? What is the pool?
The pool represents if I just ran the algorithm, like in my head. So let's say I didn't have Oracle access, but I ran him and I just simulated the Oracle queries myself. So in the beginning, I just have the all no, or like the Oracle that's always 0. After one round, I have the Oracle that's like x1. So the pool represents like doing the simulation without actually making any Oracle queries. Yeah, so just to drive one point home, the important fact that I didn't mention, but the important fact about this proof is that because he got a classical witness, I'm able to do this reusing him thing. So like every time he gives me a point, I'm able to like put him back in the pool, or like run him again with a different simulated Oracle, where I use information from the last round. If he had a quantum proof, or so if he had some proof that he had to destroy in order to catch a fish, then after the first round, he would not have this proof. So the second time I go to put him in the ocean to try to learn x2, he would just complain. He'd be like, well, I destroyed my quantum proof. It doesn't work anymore. So I don't know. I can't distinguish between the two oceans anymore. So, yeah. Okay.
One question. So
yeah.
One thing that's slightly confusing is that even in the QCMA case where he gets the map, right? The map is allowed to depend on the whole Oracle.
Yeah.
How does that work with this? Like you're simulating him now with this like fake Oracle you're cooking up that doesn't have any fish in it. It's like, how do you know that? Yeah, I don't know.
Yeah, so it's like, assume that he had the map that would work for some yes case. Then he will catch like many fish.
Yeah.
And sort of the point is like, we're going to do this simulation. And it's kind of like, if he had the correct proof for one particular yes case, then he would catch many fish from that particular yes case. But what that means is that if you imagine like running him with a random proof, like and here we'll do the same strategy of guessing the proof, but only at the end. So after we've like tried running him many times, we'll like consider this whole algorithm that catches many fish, and then guess the single proof to that. And the point is, like, you can imagine this proof will be like a very small string, a poly-n size string, and that string, that little tiny string, somehow has to like match up to like doubly exponentially many possible yes instances. And so like for every like ocean S, every big ocean S with L fish, there should be some proof that like lets him catch many fish. And instead of like guessing the location of the fish, I just have to guess this like very tiny map that he would like need to catch all these fish. And that's where the contradiction lies. Somehow there's many more oceans than there can be proofs. And by having this like multi-fisher or sampler, I'm able to like just guess that little tiny proof to find like almost all the fish in the ocean. Yeah. Okay. So anyways, the point of all that was to say this set size problem is outside of QCMA. Separately, for those of you who might know, this is a problem in AM, the class AM. But unfortunately, it's also not in QMA. So this doesn't work. This is not a separation. Actually, this paper by Aronson, Kothari, Kretschmer, and Thaler is, I think, a very underappreciated paper. It's like an insane, like, it does some crazy stuff with Laurent polynomials. So I recommend reading it. But we're going to have to do a little bit more work to get this problem back into QMA. And I think I'm too slow with my talk, so maybe I'll have to start moving a little faster. But there's two ideas that I'll talk about for getting this problem to be back in QMA. So this set size problem, not in QMA, but it is outside of QCMA. And we would like to have a similar problem that we can also argue is outside of QCMA that is actually in QMA. So we're going to put this back into QMA. The first idea is to add a second ocean. Okay? And here the ocean should be sort of correlated to the Fourier transform of S. So for those of you who know like the correlation problem, it's kind of like a natural quantum idea to give someone like information in the standard basis and also give them information in the Fourier basis or Hadamard basis to like help the quantum algorithm out. So somehow we'll kind of give the quantum algorithm a separate oracle that they'll use to check this problem. And the second idea is maybe a little less intuitive to people who do quantum complexity, but I think it's almost natural to people who do cryptography. It's kind of like if you've seen the idea of one-shot signatures. It's like instead of letting him just fish, we're going to ask him to give us a signature, like a kind of a key, every time he goes to fish. And somehow that key will it'll be something he can make with a quantum proof, but he can't make without that proof. So the only way for the quantum algorithm, the quantum algorithm will be able to kind of fish around easily. There'll be like way more fish, but you can only catch a fish if you have a particular quantum state. And this we'll call this problem code intersection, but for reasons that will become clear. Okay, so I'm going to start with the first problem, and unfortunately the fishermen are going to go away, and it'll become these more diagrammatic images. But this problem, we call it spectral correlation. It's kind of related to like XZ Hamiltonian, but basically it's a problem about pairs of sets. So the set S, you should think of it as like in the standard basis, so I think of it as on the floor, and the set U, you should think of it as like in the Hadamard basis, or like it's only meaningful if you query after having done a Hadamard. And we say that these two sets are spectrally correlated if there is some state psi, and psi is mostly supported on S. That means like, when I write psi in the standard basis, like sum over x alpha xx, the strings in S contain most of the probability mass. And then also the Fourier transform of psi, and here when I say Fourier transform, I mean Hadamard transform, but you could also define this problem for other Fourier transforms. But the Fourier transform of the state psi is mostly supported on U. So when I take the Fourier transform of the state and look at the decomposition, most of the mass is on U. Okay, so this is what I mean when I say two sets are spectrally correlated. And the problem is just given oracle access to these two sets, are they spectrally correlated or not? So there'll be like some two constants, there'll be some promise gap, but it's not too important for the purposes of this talk. The first thing you can see is that I've fixed this problem, right? So I have found a problem that's in QMA now. So there's a very simple algorithm. The algorithm is just first measure check if it's supported in S. You have oracle access to the set S, so you can do a two-outcome measurement that's like, are you on S or not? And if you see the no outcome, reject. And then Fourier transform, Hadamard the state, and check if it's on U. Okay? And if both of those checks accept, then you accept. And if any of them fail, if you see the no outcome for any of those two measurements, then you should reject. Oh yeah, sorry. So this is just like an algorithm. So basically, I fixed this problem of like, is this thing in QMA now? And we'll see that we can apply the same strategy for ruling out QCMA algorithms. So the particular family of spectral correlation instances that we're going to take also have this like set size distinguishing problem. So we're going to have like a big set S or a small set S, and we're going to also give out this information about the Hadamard basis. And you can trust me that there's a similar idea to this QCMA bound that says if you did have an algorithm that was QCMA, so got a classical proof, and did solve this problem, then you would get a sampler that looked at the U oracle and found many points in the S oracle. So it's very similar to the argument I gave you before, except the whole time the fisher also has access to this U oracle. Okay, that's the part you've already seen, and the part you haven't seen yet is, why do only a few queries to the U oracle not help you sample points from S? So this is like the bulk of the paper is proving that like even when I give the fisher access to, or when I give the sampler access to this like Hadamard transform of the set S, it still can't sample many, many points. In the original case, it was like very easy to see because like they didn't get anything, right? They just got this one proof that I could guess, and they found many, many fish. Here they get this oracle U that technically does encode all the or like most of the information about where the set S is, but somehow only a few queries shouldn't help you. And I'll just very briefly explain some parts of the proof, but yeah, okay, so as I said, you need to like.
Can you say again what's the oracle exactly?
What's the oracle?
Yeah.
Yeah, so like, I haven't written in these slides, but basically the way that we sample these oracles is by first sampling a random set S to be sparse, so like 2 to the n over 2 points from this set, and then we look this U oracle. We like compute some probabilities basically by taking like bra y h tensor n ket S for the like subset state for S, and we just like define some nice function like e to the minus this thing squared, and we sample points in U proportional to that number. So think of it like it's like more likely to have a point if the Fourier transform of the set S has a higher probability on that point. Yeah. Okay. So yeah, anyway, so like I said, the point is from that question is that, sorry about leaving this out of the slides, but U is going to be points are going to be more likely to be in U if they would appear with higher probability if you measured the Fourier transform of the subset state ket S. And we need to understand, in order to get this proof, we need to understand what querying U tells us about S. Okay? We do this with the compressed oracle method. So for those of you who haven't seen it before, it's basically a quantum analog of lazy sampling. So if you want to understand what does an algorithm know about some function, classically, we would do this lazy sampling approach where we only write down the points where the algorithm queried, and sort of the thing that we wrote down captures everything they could know. Quantumly, there's every time they query, we write down we generate a random answer, we write it down, we give it back to them. There's a quantum technique, it's called the compressed oracle technique. I won't explain too much about it, but you can think of it as doing a similar thing but in superposition. So every time they make a query, we kind of post-select, or not post-select, but we will make some measurement on our state and send them back the result, and we'll just have to be entangled to them. So they can make queries in superposition, and in superposition we'll measure our state, send it back to them. But the point is there's a way to be consistent even when the sampler, the algorithm, is uncomputing their queries, for example. And it turns out that in this problem, the correct thing to do, the correct way to do this compression, is using this idea from physics called bosons, which you can think of as just the quantum analog of multisets. So bosons are these particles that are allowed to be in the same mode, which is why they're multisets. You could have a set with multiple of the same element. But they've been studied quite a lot in physics. They seem to describe the ways that photons and other particles work. And the thing that we have to do, and this is all very high level, so I'll try to if you're confused, come find me afterwards. I'm happy to explain and write on a board, but it is quite a lot to write. The thing that we have to do is when someone queries at a point y, we kind of bounce two of these bosons off in the momentum basis. Yeah. The way you should think of it is position is to momentum as the standard basis is to the Hadamard basis. So querying something about the Hadamard basis changes the momentum of the particles, but not their positions. Okay? And there's a very long proof that basically says as long as these bosons remain paired up, you can't find their positions, and almost certainly they'll be paired up, so we get a contradiction. Okay, I think that's as much as I want to say about this one, this oracle separation, and I'll move on to the set size problem. Okay. So if you remember from the before I started talking about spectral correlation, we had this problem of distinguishing between big and small sets. Okay? And that problem was not in QMA, but what we can do is we can make the set very not sparse, right? If we made the set either all the points are in S or half of the points are in S, this would become a very easy problem because you could just check you could just query a random point and see, oh, is it in S? And in the yes case, you'd always see yes, and in the no case, you would see no half the time. Okay? But to make this problem hard again, we will add some kind of signing procedure. So the only way to check a point, the only way to actually query a point is to give the oracle x and some signature of x. Okay? And otherwise the oracle will say no. And the point is we want to make this signing procedure something that you can do with the quantum state, but you can't do without a quantum state. Just to be a little more formal, again, this problem is a little less natural to describe, but the signing procedure is basically going to be, given a point x, a valid signature of x is a code word of a particular error correcting code that also hashes to x. Okay, so you can think of it I have a hash function in the sky, and everyone knows about some linear code. And in order to query the oracle at a point x, you also have to find me a code word that has the correct hash. Okay? And we construct this hash using these these individual if we construct it as a product of many, many small hashes, this is just for the purposes of the quantum algorithm. Okay? Hopefully that makes sense to everyone. Basically, we've modified the problem to make it, in some sense, easier. The points x will not be sparse anymore. So if you could sign every point, it would be very easy to solve this problem. But we've also added the signature that we hope will make it really hard to sign. Hi.
Is the idea like you have to attach a proof of quantumness to each query?
Yeah, exactly. Or yeah, basically there'll be some like proof of quantumness. Like the only way to generate the signature will be with a particular quantum state, and so the quantum algorithm will be able to basically have like free access to the underlying oracle, and we'll separately have a proof that like no one, like if you didn't have this quantum state, then it would be really hard to sign this oracle, and if you don't have the signature, then it's very hard to distinguish between the two cases. Yeah.
Would this work for like any general verifiable proof of quantumness?
So the lower bound is where we have to use this particular form. I guess like morally, yeah, if you had like any proof of quantumness, like yeah, you would hope that you could get a contradiction just by saying, oh, if there was a QCMA algorithm, then you would have broken your proof of quantumness. There's a subtlety, which is that like, usually when you define a proof of quantumness, you only define soundness relative to like efficient algorithms. So like you would have to have a QCMA, a proof of quantumness that's sound against QCMA, but QCMA still contains VQP, so it's like, yeah, there's subtlety there, but yeah, kind of morally it feels like that. Okay.
Wait, just a question. How big should I be thinking of these sets now? Is it like I'm distinguishing like half of the domain versus a quarter of the domain, or like?
Yeah, like that. Or you can think of it like all of the domain versus like half of the domain, or a third of the domain, or something. Yeah.
Are you going to say how the QMA algorithm actually does this, or?
Yeah,
Okay.
I'm gonna tell you how the QMA algorithm does this. Well, again, I'm gonna say it in like a very hand-wavy way, but so this is formally the problem. So I have this oracle access some signed set guy. So he has a set S, and he also has these like hash functions, F1 through Fn, and everyone knows about C, because everyone knows about C. And I just ask you, is this set S like really, really big, so everything, or is it a third of things? So like I said, if there weren't these hash functions, this would be a BPP problem. Someone could just query like a random point and distinguish between these two with like advantage like 2/3. But the point is that this like signature will make it really hard to query points for anyone who doesn't have a particular quantum proof. Okay. Let me just argue why this problem is in QMA, and it kind of like revolves around this algorithm discovered by Yamaka and Zandri, which is based on this regEvs reduction for lattice problems. So this is the state that the prover wants to receive. So like for every index I, remember we had written down this hash function as like a product of little hash functions. So the prover expects to get like these pre-image states, like all of the xi's, like all the pieces for one component that map to 0 and then map to 1, right? And the point is like if they have a string x that they want to check, they'll like construct the correct state and then perform this Yamaka-Zandri algorithm, which is basically like realizing the convolution trick. So if you think about it, the reason we call it code intersection is because it's like the intersection of a linear code and these like hash functions. And this Yamaka-Zandri algorithm is kind of like a way that quantum algorithms can implement this convolution trick, which allows them to compute the intersection of two states, like the pointwise product of two states. When one of these is like the superposition over code words of a code, and the other one is like superposition over like things that have the correct hash, then you see that like this state is like exactly things that are in the code and have the correct hash. And the point is that there's this nice trick from math that says that actually you can implement this state if you could prepare the convolution of the quantum Fourier transforms of those two states. Okay? And what does it mean to do convolution? Convolution is basically just like C-naughting, or like controlled adding and then decoding. So in reality, the convolution is like sum over x and y of like the amplitude at x and y. But if I could prepare like sum over x and y of like x comma x plus y and then uncompute x, I would get the same state. And so this Yamaka-Zandri algorithm is basically like Fourier transform both states, add them together, and then like decode one of the two states. And that's where the linear code comes in. Okay, so basically using this algorithm, having received this state, a quantum algorithm can like sign any message it wants. So given any x it comes up with in its head, it can generate the signature using this algorithm. And then once you can do this, it's very easy to solve this problem. You just pick a random point, check using this signing algorithm, the Yamakai-Zandri algorithm, if the point's in the oracle. And if you ever see like no, then you know that you have a no instance. Okay. Separately, we can apply a very similar argument for ruling out QCMA algorithms. So again, we're going to do the sampler argument. There's only like one oracle now. And if you remember, the thing we said is like, if you could distinguish no from yes, then you must have like found one point like and its signature, right? So now the point is that like if your QCMA algorithm actually distinguish between these two, it must be able to sign one point. It must have one x comma signing of x. And again, we can do this trick where we add the point back to the oracle, ask it again and again and again. And the point is we'll get many, many points, like x and their signatures. Okay? But this alone is not enough to rule out QCMA algorithms. So for example, if the linear code was like trivial, if it was everything, then there would be like a really short way to sign every message just by like receiving 2n preimages, and you just like mix and match them. Like if this code didn't restrict you to like having an interesting signature, then you would just need like a few bits to sign every message. Like for every 0 or 1, like tell me the like one symbol that hashes to 0 and hashes to 1, and I can like mix and match them to get every string. So the interesting part about this is that we're going to have to like find a nice code for which like if you found many like x's and their signatures, so like the other way to think of it is like a signature and the hash of that signature, then you must have also like found many hashes. So you must have like guessed the hash for many different strings. Okay? It turns out that this quantity, like how many symbols you have to know in order to construct many code words, is exactly called the list recoverability of a code. Okay? There's actually the way that you would define it normally is like kind of reverse. Like given the symbols, how many code words must you be able to construct from them? But we'll think about it in this converse way for this problem. And when I say near optimal list recovery, I mean that like if I give you any collection of L code words, you must have like L times little n many symbols. And we can just quickly see that like so theorem 1 says that like if you had a QCMA algorithm, then you would have this sampler that outputs for you like many code words, so many like signatures and their hashes. And theorem 2 says that in order to guess the hashes of the code words, you must also have guessed the hashes of like L times n many symbols. So you had to guess like many random bits. And together these two imply a contradiction. Okay? So you see the main thing that we need to find is a code word that has really good list recoverability. Actually, to get this whole thing to work, you need like good enough distance for the dual code, and you need the dual to be efficiently decodable. Okay, not really, because really you can add another oracle that like decodes the dual for you, but those are like getting in details. But you also need these two additional properties for the code in addition to this like really good list recoverability. And it turns out there is a family of codes, these multiplicity codes that have all these properties, so we get a separation. Before I like wrap up this talk, I'll just briefly say like I wanted to have a slide here that was like what's like like looking at these two oracles, like where do they both use like two bases? Because the second oracle is kind of like really hard to see like why there's a second basis, or like because the oracle is just checking something classically, it's just like checking a signature. In the first oracle, it's very easy to see that like there's this like destructive measurement that's happening, right? Like there's a second Fourier basis that like if you were to like only receive some, if you like were to measure your state, it would like destroy the coherence that you would need to check this like second measurement. Like sort of in the Hadamard basis, you would like have destroyed the information. A similar thing is actually happening here with this Yamakar-Zandri based approach, but it's a little more subtle. The point is sort of like this convolution trick. Like if you measured a single, like let's say someone handed you like one code word X and its signature. So like the prover came and was like, here's how you can sign 1 point. And you wanted to like use this to sign another point. A natural thing to try would be, let me just try undoing this algorithm, right? Let me try to recover sort of the state that I would have gotten, right? Like the actual state. Because I had one signature, maybe I can just like pull it back, like reverse the whole algorithm and try to recover the witness from this signature. And sort of what happens, even just running it forward, is you see that like the point of this convolution trick is like actually the phases of that state like matter a lot. So like there is a second basis here, and it's because when you go to do this convolution trick, like you have these phases. And the interesting thing is that like one of the reasons why we need good distance for these codes is because we like need these states to have support on the zero string in the Hadamard basis. It's sort of like very important that like in order to be able to decode this state, we need these strings to look like low Hamming weight strings in the Hadamard basis. But low Hamming weight strings have to be, in the Hadamard basis, have to be really big superpositions in the standard basis. Like the all zero string in the Hadamard basis is like superposition over all things. So yeah, I don't know. I couldn't like formalize this into a single slide, but there is like something interesting going on where like because of the constraint that we have to decode this thing, this state has to be like low Hamming weight in the Hadamard basis, and that means it has to be a very large superposition in the standard basis. So there is like something going on here, but yeah, I just wanted to point that out, but I didn't actually make a slide about it because it was too tough. Okay, so now just to wrap things up, I think I'm close to out of time, unfortunately, but some problems are only meant to be proven once. Sort of what we argue is that like if you could have a clonable proof for like these problems, spectral correlation and code intersection, you would arrive at a contradiction. You would have something that we know you couldn't have. But it's kind of like these quantum proofs are so powerful that you can only use them once. Otherwise, they lead to contradictions. But sometimes that's a good thing. I mentioned at the beginning of the talk that like part of the motivation for studying QMA versus QCMA is that we actually want to understand like why things are not clonable, because oftentimes we want to use that unclonability to like do something that would be impossible classically. I'll give you two examples. The first one is publicly verifiable quantum money, which very much looks like QMA, like the QMA versus QCMA schemes, in the sense that there's like a verifier that's efficient that can like check some quantum state. The difference is this state doesn't have to be efficient to generate anymore. But quantum money is this idea that you can have a quantum state that you can check, so you can check the validity of, but it would be hard to counterfeit or clone it. And the second place I think this is kind of has intersection to is like verifying quantum computation classically. So almost every classical verification of quantum computation algorithm in the proof has some step that kind of goes like, at some point in the proof, the quantum computer should have some particular state, and if they had some classical representation of the state, they would be able to like repeat some measurement or repeat some procedure, and then you would break some cryptography. So a very similar thing happens here, where you have this verifier who wants to make sure that some particular part of a quantum algorithm is like hard to clone. In many of these settings, we want this unclonability, which appears in this, it kind of like relates to what I think of as a sampler argument. But of course, I'm not claiming to solve any of these problems. These are still like super hard problems. Kind of like, I was going to make a joke here. It's kind of like sailing in an ocean or trying to figure out how many fish there are in the ocean. But I also felt like I should include some like more realistic problems for any students who like want to like think about ways to extend this result, or like things that they could like reasonably solve. I included 3 here, so I'll just quickly go through them. The first one is QMA search decision. I think this is a super interesting problem. It kind of also relates to like the relative power of like classical like computation. So it's kind of like asking like, if I gave you the power to solve any problem in QMA, could you find the ground state for that problem? I think the answer is no, and there's a quantum oracle separation, very similar to QMA versus QCMA. So making that into a classical oracle separation would be pretty cool. The natural like next step, I think, for QMA versus QCMA is this communication complexity setting. And some people might refer to our work as like solving the query complexity of QMA versus QCMA. But you can also imagine like a setting where you have 2 parties that want to compute some joint input on some on their input, the joint function, so f of x and y, on their two inputs, and they get the help of either a prover whose quantum gets to send them a quantum proof or classical proof. Typically, like bounds from communication complexity lift to query complexity, but not the other way. So it's interesting to try to extend these results there. And then finally, there's this problem of originally BQP versus IP, which is kind of an extension of the Rosenthal like BQP versus pH. But I think it might be a little easier if you talk about QMA versus IP and try to use the spectral correlation problem to try to prove that the spectral correlation problem is outside of IP. You know, I think it's just like maybe slightly easier than trying to prove that correlation is outside of IP. So I don't know how to do this, but this is just a candidate. Spectral correlation, I think, is a promising candidate for showing one of these separations. So
I noticed that QMA is known to be in p-space. What do you mean by that?
oh yeah, so it's known to be in p-space, but not necessarily relativizing.
Oh, okay.
So you could still hope to find an oracle relative to which, so it's known to be in p-space, but like relative to an oracle, it might not be in IP. So you could still hope to separate them. Yeah. Yeah. Okay. Oh, that's all I had. Sorry for going over. Oh, hi.
For the communication complexity problem, are these people are still bounded computation, right?
So you typically, in communication complexity, you could imagine that they're unbounded, but they only want to send polylog n bits of communication.
Yeah.
So,
But
yeah.
So you're saying in that is still the case for this problem?
Yeah.
They're like unbounded, like they're infinitely powerful.
Yeah, like locally they could do anything.
But this is like kind of seems different than QMA versus QCMA, right? Where it's kind of, you know, you have.
So I mean, in the version that we talked about, like you could also imagine, and we also ruled this out, like if the verifier is locally like unbounded, they're only bounded in terms of like the queries they get to make, they make to the oracle. So in that regard, there's a connection there, but yeah, I'm not an expert on communication complexity. I just think it's like a natural like next step. Yeah. Hi.
I had a question, which is, so I know previous people looked at this Yamakawa's Andrew problem as a candidate for separating QMA and QCMA.
Mm-hmm.
Do you have a sense of like what was the idea that kind of unlocked it? Like, because like people weren't able to show it, and then you guys were able to like.
Yeah.
Yeah.
That whole thing happened really quickly, and it was kind of just like this observation that you should apply this sampling argument to this problem. So I think people in the past had basically tried to argue something along the lines of like a big hybrid argument. It's like we're going to take this oracle, we're going to like puncture it, like remove some of the points and try to argue that's indistinguishable, and then like repeatedly do this. I think like when I first like talked to Andrew about this, I was like, oh, why don't we try doing this sampling argument? And it kind of just popped out like, oh, look, like the thing you sample are not really like the points that are hard to guess, but they're like these code words. And then we like went on this hunt for like list recoverable like codes with really good list recoverability. But yeah, I think like the main thing was just like, oh, we should apply this sampling argument to this new problem and see what comes out of it.
Thanks.
Okay, maybe I'll get to it. Sure.
So I have a question that's maybe a little bit far. So we know that QMA, the complete problem is local Hamiltonians. So these are things that are can be described by polynomially many parameters, but the quantum states could be the ground states could be extremely complicated, require more than polynomial size quantum circuits. And for QCMA, a complete problem could be, one of the complete problems is local Hamiltonians whose ground states are generated by polynomial size quantum circuits.
Mm-hmm.
So can you come up from this separation result to a suggestion of a class of Hamiltonians, local Hamiltonians, whose ground states are extremely hard to, cannot be generated in polynomial time?
Something I like to imagine is like, classically when people like imagine like what does it mean, like people talk about like, one evidence people have for like SAT being really hard is like, well, it would be impossible to like solve SAT if you just had a random function, like to find any preimage of 1 for a sparse random function. And sort of the thing that tells you is like, anyway, it just tells you like, unless you're using like some structure about the SAT instance, like you won't be able to solve it. Anyways, but one way that I would like to imagine someone could have come up with a spectral correlation oracle is if they just like stared at like XZ local Hamiltonian, and they were like, well, what if my X basis was like a SAT instance? So like it's like just like in the X basis I'm describing a SAT instance, and in the Z basis I'm also describing a SAT instance, but maybe an easy one. Then if I imagined that I didn't actually look at those SAT instances, so they're just now like 2 functions. Like one of them is like preimages of, I need to find preimages of the first function in the standard basis, and I also need to find preimages of the second function in the Hadamard basis. Then you would basically arrive at the spectral correlation oracle. So if I had to guess how you could find these hard instances, I would say maybe like try finding like pairs of SAT instances, like one in the standard basis, one in the Hadamard basis. And my guess would be if these are like hard SAT instances, or whatever that means. I don't know what people have for like candidate hard SAT instances, but my guess would be those would give you like these hard spectral correlation instances.
Great talk. Thanks, John.
Oh, thank you.
So this might be a bit technical, so maybe we take it offline, but I didn't understand in the code version why you need this sampling problem. Like it seems like you're saying something very strong, which is that like you can only make one query or something with a okay, maybe it's you need like maybe the I guess the proof can encode multiple signatures. Is that what you're saying?
So
but
it's like
not
if you
that
had a
many.
classical proof,
Yeah.
then it would kind of be like I took your one-shot signature and I made it repeatable.
Yeah.
I could rerun it. And so that's kind of the point, is like to assume for the sake of contradiction that like this thing we thought was only doable once, this one like signing procedure, imagine you could do it many, many times.
I see. So you need a problem that you need like more than one query to solve. Is that? Like,
No.
Like the sampling problem, I guess I
the
didn't
sampling
understand
problem
what the
is-
sampling problem was doing. There.
Yeah.
So that's just like you need a problem that needs multiple queries to solve.
Yeah, like it will need multiple queries, like even like no matter what. But yeah.
Okay. Thanks.
Yeah, thanks for the talk. Do you see any potential for these techniques to be applied to, like, say, like getting an oracle separation between QMA2 and QCMA and QMA? Sorry, QMA2 being like the problem of like two Merlins.
Yeah, I'm aware. I think studying QMA2 versus QMA is an amazing question. I have very little insight into like how you could solve it, unfortunately. Yeah.
Thanks for the talk. Yeah.
Any other questions? Okay, thanks, John. So we'll reconvene after coffee break at 11.